Yes, I'm recording. What other forces are acting on these objects?
You got tension force times 4.
I have 4 of them. How do you figure?
No, I mean like you got one up, one
Okay, so I've got one up here.
Yeah.
That's FT.
Yeah, and you got one to balance it.
So there's an FT here.
Yeah, and then you got another 2 up.
I have another 2 up.
No, I'm on the top. Whoa.
I'm going to call these FT1. I'm going to call this one FT2 because they're going to be different tensions. We don't have a tension down. Because, why? It's, as far as we know, it's not attached to anything. So yes, somewhere we're going to have tension somewhere. But as far as the free body diagrams go, for the objects that we have, this is the free body diagram. So we're also told what? The thing is at rest. And the last thing we should throw down on this diagram is what? Which way do you want positive to be, Jasmine? You said up was positive. Cool. So then, let's write out the equation. I have F net equals MA, but A is going to be 0. What if up is positive, what's the F net expression going to be? Sorry? FT what minus FT what? Sorry, FT1. FT2 is acting up, so that's positive. Minus FG. I'll call this FG2, and I'll call this FG1. So FT2 minus FG2. Hold on, no, we have to do it for the whole system. We have to do it for the whole system. Actually, so you're analyzing it just for this one?
Yeah.
So then this one has an FT2 upwards and an FG2 downwards and an FT1 downwards. So FT1 needs to show up here. Right? So this is going to be minus FT1 equals 0, because A is 0. So you could do it. You could separate them up and analyze them individually, sure, because we know the acceleration. So that means that FT2 is going to equal 98 plus FT1, and we don't know FT1. So let's go through now and find FT1. Let's analyze the other block. What's the F net equation going to be for the other block?
FT minus FG equals MA.
FT1 minus FG equals 0. So that's going to be FT1 minus 196 equals 0. So FT1 is going to equal 196 newtons. So there's that tension. And to find the other tension, you just take that value for FT1 and plug it into the other equation. So we're going to have 98 plus 196. So FT2 is going to equal what? Almost 300? 394? 294. Almost 300. I have a feeling, Jasmine, you ignored that guy right there.
Yeah.
Cool? Comments, questions, concerns? Okay. So that's question 7. We could have done it as one big system. If we would have done it as one big system, we would have found FT2 first, and then we could have gone through and found FT1. But other than that, yeah, that's number 7. Number 8. Eric, you asked 8? Okay. What is the tension in the rope that joins the two blocks that are pulled by a constant force of 500 newtons in the diagram below? So the diagram below looks like this. I've got a block, I've got a rope, I've got a block, they're on the ground, I've got a rope pulling that way. This guy weighs 10 kilograms. This guy weighs 20 kilograms. This guy, oh, we're told that the coefficient of friction is 0.12. So what forces are acting on our objects? Gravity is acting downwards on both. This FG, I'm going to call this FG. I'll call this block 1. I'm going to call this block 2. So FG1 is going to equal 98 newtons. What other forces are acting? Gravity on the other one, so that's going to be FG from block 2 is 196. Acting which way? So which block are you talking about? Both of them. Okay. So that guy's going to have a force of friction. I'll call that F force of friction 1. This guy's going to have a force of friction. I'm going to call him force of friction 2. We're going to have an Fn, which is the same as gravity.
Take the gravity, multiply it by the mu, or 0.12.
Just to recall, I'll throw it down here as Connor is saying it. Force of friction is mu Fn. So the force of friction here is going to be 0.12 times 98, which is 11.76. And this guy is going to be 23.52. Love it. What other forces are acting on these objects? Tension in the middle of the two blocks. So I'm going to call this force of tension, and I'm going to call this guy force of tension. They are the same because it is the same rope. And I'm not going to call that tension. I'm going to call it an applied force, just for the sake of keeping things straight here. Because that's the force that's being applied to the system. That guy's going that way. So those are all of the forces acting on these objects. And we want to find what? The tension. So to find the tension, what are we going to have to find first? The acceleration of the system. To find the acceleration of the system, we have to treat these objects as if they were one system. So F net equals ma. What forces are acting? So, oh, we're missing one more thing yet again. Positive to the right makes a lot of sense. Okay, so then what is my F net expression going to be for the system?
A minus FF equals
Which FF? FA minus, you said FF, which one?
like I put both together.
Oh, you added the frictions together.
Yeah.
Because they're acting in the same way to the left? Well, for the sake of what I'm going to write down, I'm just going to write them down separately, but they're both being subtracted then. Okay, what else am I doing in here?
Equals 10.
Oh, there's more forces.
Oh, there is the cancel.
Yeah, these guys are going to cancel. Minus FT plus FT equals 30A. So these are going to cancel. I know they're going to cancel. I know some of you know it's going to cancel, but I want to see it anyway. So this is going to be 500 minus 23.52 minus 11.76 equals 30A. What's A?
15.49.
15.49 meters per second squared equals A. Cool. That's the acceleration of the system. Then to find tension, we isolate one block. Which block do you want to isolate? Left one makes more sense. There's less going on with the left block. So we're going to isolate block 1. So now I'm going to get F net equals ma. The forces acting in the direction of motion for block 1 are what?
FT
And that minus F.
And we're going to subtract that force of friction equals MA. So then FT, the tension that we're looking for in that rope, minus 11.76 is going to equal 10 times 15.49. So then my tension is going to equal 154.9 plus 11.76. $167, give or take. That's what you got? Plus or minus something. Okay. 166.66. Okay. Make sense, Eric? Okay. And then number 9, Jasmine, was that you? Who asked number 9? You think it was you because you didn't do it? Oh, so you attempted it, but it doesn't make any sense. Okay, let's look at number 9. Safety engineers estimate that an elevator, which is where we're going today, that's cool. Elevators can hold 15 persons of 80 kilograms average mass. Oh, a particular elevator can hold 15 persons of 80 kilograms average mass. The elevator itself has a mass of 500 kilos. Tensile strength shows the cable supporting the elevator can withstand a maximum force of 2.85 times 10 to the 4 newtons. What is the greatest acceleration the elevator can attain without breaking the cable? So, there's my elevator, here's my cable.
Correct me if I'm wrong, screwed up, but that's like with the full load, right?
That's why they told us 15 people, 80 kilograms, yeah.
Yeah, yeah.
So, this then, I need to draw my forces. Gravity for the elevator. Fg for the elevator is going to be 500 kilograms times 9.8, given the information in the question.
Well, and then you also gotta add the people. Oh, shoot.
Plus
Plus 15 times 80 per
15 people times 80 per person times 9.8.
All of it combined is 16660.
1660.
That is an extra 6.
16,660 newtons.
Yeah.
Okay. So we are told that the max, and tension is going to be acting up because that's where the cable is pulling. The maximum tension that this thing can hold is 2.85 times 10 to the 4 newtons, which for the sake of keeping things consistent with, between these two, that's 28,500. Yeah, newtons. And I want to know the maximum acceleration. Now, the maximum acceleration is going to involve the maximum possible tension force. So we're going to assume that the force of tension, is this maximum force. And for this thing to exert this maximum force, this thing's going to be accelerating which way? Take a look at the forces. Which one's bigger? This one's bigger than this one. So which way does the elevator have to be going? Has to be going up. So I'm going to call that direction positive. So then this is just F net equals MA. It's going to become FT minus FG equals MA. So that's going to be 28,500 newtons minus 16,660 equals, what is that total mass? 500. You said this was 1,700 and something?
1700.
exactly? Cool. So what's A?
6.96.
Meters per second squared. Does it mean, does that make sense? The procedure? I mean, this thing has to be accelerating upwards. What's the maximum acceleration that an elevator can experience downwards? 9.8. Means someone cut the cable and the elevator's in free fall. All of a sudden, those 15 people at 80 kilograms each are going to become become one big mass of 15 times 80 when that elevator hits the bottom. It's going to be gross. Just mangled bodies.
The elevator question. Will we like answer like the question, because this is kind of like the question of all of that. If the elevator goes into a free fall and you are both accelerating at 9.8 meters a second squared and you fall, if you jump off the or not jump off the elevator, but if you jump that elevator, like
How are you going to jump?
like as it's free falling down to the ground, if
Yeah.
you jump off the elevator.
But if it's free falling and you're free falling, are you even touching the bottom?
What do you mean?
If you're in free fall with the elevator,
Yeah.
are your feet touching the ground?
You're not touching ground.
If you and the elevator are in free fall together,
Yes.
there's a very real possibility that you're not touching any of the walls of the elevator. So your question is going to be, can you jump at the last second?
Yes.
Let's think my question is, does that question even matter? Because you're going to hit the ground at whatever speed it would be like you're not even in the elevator. You're going to hit the bottom of the elevator at that speed. It's like I pushed you off a building.
Right.
You're going to hit the ground that hard. If you manage to push up at the instant before impact, does it even matter because you've got the top of the elevator coming down on top of you?
That's a good point.
So I mean, that's my way of dodging the actual question that you're trying to ask. You're trying to ask, assuming that that's not there, you're in some open basket. Can I push up hard enough to prevent myself from becoming mush at the bottom? That would depend on how far you're falling. The amount that you're going to push up, I'm going to suggest is going to be negligible. I'm going to say no. There is no way you're recovering from a free falling elevator. It's going to be rough for you. If for no other reason that the elevator has a roof that's coming down on you, and that roof is heavy because it's got pulleys and crap on there. It's going to be a bad scene. It's going to be rough.
There's no way to survive this thing?
No. Well, unless you're not falling far enough. The only way to survive is hope that you're not falling far enough.
Wait, hang on.
Assuming that the brakes don't kick in. Because the elevators all have like auto braking and that there's punches into the walls and it keeps it there.
That's kind of weird. But what about like if there's like springs at the bottom? Like how would that affect?
It's still going to suck.
Yeah, I figured.
Because again, if you're truly in free fall, springs on the bottom, will that make it worse?
Like I mean, like
No, springs on the bottom will make it a little bit better because they'll catch you a little bit.
Yeah, but you'd almost have to be like laying flat to balance the force.
I think your best chance is to be laying flat, yes,
Yeah.
on the thing. Either way, it's going to suck. But laying flat on the floor of the elevator, assuming you can get there, assuming you aren't like completely floating in the middle of the elevator, which is totally possible. If you and it are truly in free fall, I can show you a video of what that looks like.
Yeah. You know what? You're right because I keep screwing up and I keep thinking that the weight of the elevator will make it fall faster, but it won't.
So where's what I need here? Let's talk about elevators. This one. Here we go. So when a person is accelerating upwards or downwards, which you all have done, elevators do this fairly gradually. So you might only notice it a little bit in an elevator because elevators are designed to safely transport people up and down, and so they don't want to, fling people into the air or drop the floor out from under them. Imagine your like elderly grandmother
Starts flooding.
in one of these elevators that just shoots down to the bottom, right?
That's the problem.
But you can still feel the pressure, like there's some buildings in New York that are too high, and when you're in the elevator, you can feel like in your ears something.
Oh, your ears.
Yeah, it's like driving up a mountain. Yep. Unrelated. When a person is accelerating upwards or downwards, they can feel heavier. When I say feel heavier, this is what we're talking about here as far as apparent weight goes. Apparent weight is how you perceive your weight. Okay? So you can feel heavier or lighter than you actually are depending on the circumstances surrounding you. If you've ever been on a roller coaster, if you've ever been on an elevator, you've experienced this whether you recognize it or not. If before the flood happened here and the Abbey Mission Highway had that really big bump in it, kind of by Bateman Park, no, Wilban Creek Park is what the park is called. If you were driving fast enough down the Abbey Mission Highway heading north towards Mission, there was a big bump there and you could like get a little bit of air in your seat before coming back down. This is the same kind of idea. Although your actual weight being the force of gravity on you, m times g, is the same. That's not going anywhere. Their apparent weight differs. How you experience your weight is different. Apparent weight, how heavy we feel, is equal to the normal force supporting you. So, I guess technically speaking here, your actual weight is still your normal force, but it's your normal force in a non-accelerating frame of reference. Like right now. You're not accelerating. I mean, unless we consider that other video I showed you. But for the sake of Newtonian physics, you're not accelerating. Your weight, what you're experiencing, is the normal force of your chairs acting up on you. You feel what you feel, then you stand up and walk around, that kind of thing. The weight you experience is the normal force of the ground. If the ground were rushing at you or falling away from you, your weight would feel different. And that's what we mean here by apparent weight. So, we're going to describe 2 times when mass appears heavier than normal. And I'm using this word mass and appearing heavier. So when does your mass, in an elevator, when does your mass, or where does your apparent weight feel heavier than your actual weight? When you're going up? Always when you're going up?
Not necessarily if you're going down.
Because eventually it feels normal.
Really fast.
Okay, so you're suggesting go down and stop.
Yeah. You're going to feel that.
And the other time you said was going up.
Yeah.
Going up always? Do you always feel heavier when the elevator goes up?
Well,
Or
it has to be going up for it to feel acceleration.
okay, so there's always a time, whether you're going up or down, that you feel totally normal. Why do you feel total? Well, we're going to talk about that part in a second here. But you're going up from rest or going down to a stop. Here, you're accelerating up. And here, you're decelerating down. In both of these cases, to cause you to accelerate up or to slow you down as you drop, a force has to act which way? So up. Okay. So in these ones, there is, I'm going to put it in bracket, or not brackets, but I'm going to quote here. There's an extra force up. When does your mass feel lighter? In an elevator. Tristan. When you go down from rest. Or when? Going up and stopping.
Technically, there is like a time time that stops going up, you have like a millisecond that you don't have weight?
Only if it stops very, very quickly.
Oh.
Like, it would have to stop so fast that you got flung. Your inertia would keep you going upwards. Elevators don't do that. People would get hurt. What's happening here as you go down from rest or up from stop? Sorry, up and stop or going down from rest. What forces have to be acting here? Where's the larger force, downwards or upwards? It has to be down, right? If you're traveling up and then come to a stop, there has to be a force downwards on the elevator. There's no force downwards on you, but there's a downwards force on the elevator. And one of the favorite answers that we like to give at the beginning of this chapter was inertia. It has everything to do with inertia. Your body wants to continue doing what it's doing even as something is slowing down the elevator. Your body wants to continue a little bit. And so you feel lighter because the elevator is slowing down faster than you are. There are 3 times when the masses, the apparent and actual weights are equal. I have 1 and 2 here. There's a third. When is your apparent weight and actual weight the same? When do you feel normal in an elevator? Yes. When it's stopped, yes. No. When your velocity is constant, either up or down. When there is no acceleration. Okay? So, up with constant v, or down with constant v. Because the elevator, in this case, with the elevator going up or down, the net force on the elevator is 0. Because the thing's not accelerating. And therefore you are also not accelerating. That means the cable is pulling up as hard as gravity is pulling down. So let's take a look at these. I'll zoom in on each one just to give us more space. A 65 kilogram person in an elevator is traveling upwards at 5 meters per second. What is their apparent weight? Let's draw it. Here's the elevator. There's you in the elevator. What forces are acting on you? There's a normal force upwards. There's gravity downwards. Yeah. Okay, so then you're included. So the elevator is going to have, I'm going to call that tension because it's a cable. And there's going to be Fg on the elevator.
The Fg of the elevator is the mass of the elevator and your mass together?
No.
No?
If we're specifying these things, we're treating them separately.
Okay.
Gravity's acting on the elevator. Gravity's also acting on you. What important piece of information have they given us in the question that's going to help us figure this out? The velocity is constant. Therefore, acceleration equals 0. Therefore, F net equals 0. Therefore, if there's no acceleration, there's no net force. If there's no net force, what must be true? They're balanced. In this case, what's balanced?
The actual weight and the apparent weight.
The actual weight and the apparent weight. So Fn and Fg then are balanced. Fn equals Fg. So then their apparent weight is going to be equal to their actual weight, which is just going to be 65 times 9.8. Which is 640, I think. 637? Cool. It's easy to ballpark, but harder to get it exact. Let's do the second one. The same 65 kilogram person is in an elevator that's accelerating upwards at 4.9 meters per second squared. What is their apparent weight? Let's draw it again. I'm going to draw it a little bit bigger. So we've got a person in the elevator. And if the elevator itself is accelerating upwards, that means the floor of the elevator is accelerating upwards with the rest. Like, it doesn't tear the elevator in half, right? So the box is accelerating as one big unit. So I'm just going to do the free body diagram for the person on the inside. What forces are acting on that person? Fg and Fn. Good. So I got an Fn up. I've got an Fg down. Fg is the same. Fg is 65 times 9.8. That's going to be 637. We know that this person is experiencing an upwards acceleration, and for the sake of this problem, I'm going to call that direction positive. For that person to accelerate up, that means Fn and Fg cannot be equal. Which one has to be bigger? If Fg were bigger, this person would be being dragged down.
But is the person not like touching the ceiling of the elevator?
They're accelerating upwards, so what has to be bigger, the upwards force or the downwards force?
Okay, upward.
The upwards force, and the upwards force is Fn. So I'm going to have Fn minus, so Fnet, equals ma, because now we've got an acceleration upwards.
Oh no, I got it, because I was thinking like Fn like would be 65 times 4.9. I was thinking that it couldn't be bigger, but this calculation is the result of the Fn.
Yes, you were ignoring one piece, yeah. So then what is Fn going to be? Do you have a value for me?
955.5.
Okay. Okay. So here's a question for you. This would be the same as if the person actually had what mass? Divide that by 9.8. What's that value? 97.5 kilos. So it would feel like this. What this feels like is if the person had gained 20 kilos, give or take, which is 44 pounds. If the person suddenly gained 44 pounds, this is what it would feel like. Accelerating upwards in an elevator at 4.9 meters per second squared. For my wife, that would be like doubling her weight. Like twice my wife instantly. That would suck for her. Okay, last one. Well, second last one. The elevator reaches the top and decelerates at 4.9 meters per second squared. What is the apparent weight? So we're going to draw it again. Now we've got a person in the elevator. Fn is still up. Fg is still down. Acceleration this time is which way? Because I'm sloppy a little bit. Acceleration is which way this time? Downwards, because it's slowing down to a stop. So I'm also going to call that direction positive in this case. So now which one should be bigger, Fn or Fg? Fg is going to be bigger for the person. So now I'm going to have Fnet equals ma. So it's now going to be Fg minus Fn equals ma. Fg is still 637 minus Fn equals 65 times 4.9. So now my Fn is going to equal the 637 minus 65 times 4.9. What is the person's apparent weight in this case? No idea, Vi. Sorry? 320.5? 318.5? I mean, effectively it's 320. So this would feel like the person actually has what mass? 32.5 kilograms. So they've halved their weight. That would be weird. Normal elevators don't accelerate this aggressively. And so what this is trying to show, what you need to recognize here is it doesn't actually matter how fast the elevator itself goes. The only part of the trip that matters is what? The speeding up and slowing down. So this explains why bullet trains in Japan are you can be totally fine in them as fast as they go. As long as they don't come to a screeching halt or take off like a rocket, it does not matter how fast the trains themselves are going. All that matters is the acceleration and the deceleration, which is kind of cool.
That's why the point of Bill in this case.
Sorry?
The point of Bill in this case, like, is just to the motion, like, really, really fast, and it doesn't do anything.
Correct. As long as you're not accelerating, you can't notice. Okay, which is why us moving on planet Earth doesn't really seem to matter, because we're not accelerating. Unless the Earth stops spinning. Then we got all. I want you to do this question here for homework. I then want you to flip the page, and I want you to do this page for homework. This is a trip on an elevator. Okay. On your market, set, giver. Yeah. You betcha.